All right, now we'll discuss some important problem types from Chapter 2. One of the first things we encounter in Chapter 2 is coming up with these nuclide symbols. And we have the atomic number, that's the number of protons in the nucleus, and that's represented by the symbol Z. Atoms are neutral, so if we don't tell you that there's a charge on the atom, the number of protons and electrons is equal. And then there's the mass number. Most atoms have some number of protons and neutrons in the nucleus. This mass number is the sum of protons plus neutrons. And it all gets put together in a symbol like this, where the X gets replaced by whatever atom we're talking about from the periodic table. The mass number A goes here at the top, and then the atomic number Z goes here at the bottom. So, and then this here at the very bottom is how we can name it. So if we were just saying it in words, we would call this carbon-12, giving just the name of the element and the mass number, because you can figure out what the atomic number is from the periodic table. Or nitrogen-14, again, name the element and then say what the mass number is, or oxygen-16. Okay, so the atomic number is the number of protons in the nucleus of any given element. You can find it on the periodic table. It's at the top. It's the integer. It's the number with no decimal, just a simple number, and it increases 1, 2, 3, 4, 5 across the periodic table. The mass number is the total number of protons and neutrons in a particular atom. The number of neutrons is then equal to the mass number minus the atomic number. They'll tell you how many neutrons are in there. And then finally, if we're talking about something that does have a charge, the number of protons minus the number of electrons will tell us what the total charge is for an atom or an ion. The next concept that we talked about in this chapter was calculating average atomic mass, and here on this slide we're going to do that for chlorine. Chlorine has two naturally occurring isotopes. You need to be given the exact mass and the percent abundance. So we're given the two exact masses that exist for chlorine and their percent abundances. We will convert those into decimals by dividing by 100. So the 75.78 divided by 100 gives us a 0.7578. The 24.22 divided by 100 gives us 0.2422. Multiply and add together, and we get now the average atomic mass of, I should say chlorine here, it's a typo. The average atomic mass of chlorine is 35.453. You can compare this with a straight average. So if we added just these two numbers together and we divided by 2, we would get 35.967. You see, this number is smaller than the straight average. It's smaller than the straight average because there's more of the lighter element. This is the lighter element. It is 3/4 of the sample roughly, whereas the heavier element is only 1/4 of the sample roughly. And so that is why the average atomic mass of bromine, this weighted average, is smaller than just the straight average we would get if we added these two numbers and divided by 2. We talked about in this chapter the anatomy of the periodic table. We go down through the stair steps here. The stair steps here in purple are the metalloids, and then the elements that we have here in green are the metals. The elements in orange, mostly grouped together here on the far right, are the nonmetals, with the exception of hydrogen, which is put here on the periodic table. It actually fit for the purposes of metals, nonmetals, and metalloids better over here in the periodic table. Here's another couple of ways of dividing up the periodic table. If we take just these first two columns plus the last 6, we can call those the main group elements. And then within the main group, some of the columns have names. So the very first column there is the alkali metals. Right next door to it is the alkaline earth metals. Far on the right side of the periodic table, we have the halogens and the noble gases. Here in the middle of the periodic table, this group of that's 10 atoms wide is the transition metals, And then down there at the bottom of the periodic table, we have the lanthanides and actinides. So if we're focused on a particular column, we might use the column name. If we're focused on a group, like the main group, we would say main group or transition metals. Or back to this previous slide, if we're interested in just metals, nonmetals, and metalloids, we could use those names. So different names that we might give depending on what our discussion is. For compounds that are composed of all nonmetal atoms, those can form molecules. And here is a molecular formula. Molecular formula shows the exact number of atoms of each element in the smallest unit of substance. These blue spheres here are nitrogen, the white spheres are hydrogen. So this has a formula of, molecular formula of N2H4. Its empirical formula is the simplest whole number ratio of atoms in the substance. So 2 to 4, like if we had a fraction that was 2 over 4, well, that would simplify to 1 over 2. 2 over 4 and 1 over 2 both are half. Likewise, this formula, C6H12O6, if we divide all those through by 6, it would simplify to CH2O. However, this one, so we have C5H6, there's no common number that we can divide both of them by. So in these instances, the molecular and empirical formula are identical to one another. There's no common factor that we can go. For the first one here, we could divide both by 2. For the second one, we could divide them all by 6. Here, if we divide the first one by 5, it's okay, but the second one we get 6 over 5, and that's not an integer. Likewise, if we divide them both by 6, the last one's okay, but the first one is 5/6. That's also not an integer. So it can't be simplified. Again, if we go to fractions, 5/6 can't be simplified to anything simpler. And likewise, even with this example here, 1 to 3, 1/3, 1 to 3 can't be simplified. So here's one way to visualize an empirical formula versus a molecular formula. For this molecule that we have here, this is, you don't need to know the name, but the name of this is cyclopropane. This was used as a dental anesthetic for years. It has the molecular formula, C3H6. There's 3 carbons, there's 6 hydrogens, but the empirical formula is CH2. So 3 to 6 versus 1 to 2, so the empirical formula is CH2 in this case. And what I want to draw your attention to is the empirical formula is contained some number of times in the molecular formula. Here, what's nice about this molecule is it's obvious that it's exactly 3 times. So I can take this molecule, divide it up into thirds. Any one of these little triangles contains the empirical formula. Here's the empirical formula, or here's the empirical formula, or here's the empirical formula. So the empirical formula is contained exactly 3 times in the molecular formula in this case. All right, so remind you, if we have all nonmetal atoms together, that's a molecular compound. If we have metalloid plus nonmetal atoms, that's molecular compound. The only exception being if we have this NH4, the ammonium cation, plus some nonmetals, that is an ionic compound. That's one of our only exceptions. If we have a metal plus nonmetals, it's always ionic. Again, normally I would ask people to memorize these prefixes. You need to make sure that you know how to use them. You could go ahead and print out something to have them at hand. However you want to do it, make sure that you're ready to use these to name compounds. And we use these in naming molecular compounds. So again, if we have nonmetal with some other nonmetals, or we have a metalloid with some nonmetals, it's a molecular compound, and we name it using these prefixes. So how do we name P2O5? Well, first we name the first element. The first element here is phosphorus, and we add a prefix to tell us how many of them of the first element is there. So this is diphosphorus. We don't use mono on the first word. On the second word, yes, but on the first word we do not use mono. The second word is the name of the element appearing second, with the ending changed to "ide." So oxygen, this is oxygen, oxygen becomes oxide. And we need to tell you how many oxygens. So 5 of them. Pent means 5, ox from oxygen, and then ide because it's the second element. So overall, this is named diphosphorus pentoxide. For some of the columns of the periodic table, the first column always has a +1 charge. The second column always has a +2. The halogens over here always have a -1. And the elements that are here, and you need to know this, again, you don't need to memorize this, but you need to have this, for example, marked on your periodic table. For these 4 elements, they always have the charges that are indicated here. For silver, zinc, cadmium, and aluminum, they always have the charges that are indicated here. However, everything else in the green here is variable charge. So for example, we can have iron 2 or iron 3. We can have cobalt 2 or cobalt 3. And so we need to do a little bit of detective work to figure out what the charge of those is. How do we name an ionic compound? Write the formula of the cation. How do we write the formula for an ionic compound? Write the formula of the cation followed by the formula of the anion, omitting charges. Use subscripts to show how many of each is there. So use the fewest number of ions possible. Calcium 2+, if it's with chlorine, has to have 2 chlorides because each Cl is Cl-. So calcium 2+, Cl-, and another Cl- is how we get our formula. If we have more than one of a polyatomic ion, then we need to use parentheses to show that. So for example, this is magnesium 2+, OH is OH-. Needs to be 2 of those for it to be neutral. And to show that there's 2 OH-, I put parentheses around the OH. But I only do that with a polyatomic. So for example, for barium bromide, there's 2 bromides as the second part of the formula. I do not put parentheses around it because it's just a single atom. So here is all our monatomic ions that we need to know the charges for. And then, as I said, other transition metals, for example, iron can exist as iron 2+ and can exist as iron 3+. How do we name an ionic compound? Name the cation, name the anion. Prefixes are never used for ionic compounds, never, ever, ever. So calcium is the first element, calcium, and then chloride. So it's not dichloride, calcium chloride. Magnesium hydroxide, name the first element and then name the second. Barium phosphate, okay, name the cation, name the anion. And here's the catch. For some ionic compounds, if they have a transition metal, we may have to do a little bit of work to figure out what the charge is. So each chloride has a -1 charge. So for this first compound, -1, -1 means this has to be iron 2. And when I tell someone the name, I say iron, and then this is Roman numeral in parentheses, chloride. Versus the second one, there's Cl-, Cl-, Cl-. There's 3 Cl-. So this must be iron 3 chloride. And then these hydrates are pretty easy to name. So we name the other piece, the non-water piece of these, as we would have. So copper 2 sulfate. Then we use a prefix to tell you how many waters are there. So copper 2 sulfate pentahydrate. 5 waters, pentahydrate. Sodium carbonate, decahydrate, to tell you that there's 10 water molecules. Iron 2 chloride, tetrahydrate. So iron 2 chloride. Here I'm working backwards. I know this iron is 2+, so there must be 2 chlorides. So FeCl2, then the dot to tell me that's a hydrate, tetrahydrate, 4 water molecules. All right, and here we'll summarize all those things. So for group A1, the alkali metal ions, they all have a +1 charge, such as lithium+. Group A2, the alkaline earth metals, have a 2+, such as magnesium 2+. Group A7 have -1, as in bromide, Br-. And then these are constant, and you need to know these or write these down. Silver has a +1, zinc and cadmium have +2, and aluminum is always +3. If this has all made sense to you, then this group is a good way to test that. So we have a bunch of chlorides, and several of these get named differently. So 1, 2, 3, 4 of the 5 of these are ionic compounds. So name the cation, name the anion. Sodium chloride. Zinc chloride. Okay, and we always know that zinc is 2+, so we don't need to tell people that. But we do in the next one. Iron 3+, so iron 3 chloride. Now we're finally at a molecular compound. So this is all non-metal atoms. So name the first one, nitrogen. Now I have to use a prefix, nitrogen trichloride. And then finally, this is the ammonium polyatomic cation. Ammonium, name the cation, name the anion, ammonium chloride. And just remember these sorts of things. Magnesium hydroxide is magnesium with parentheses around the hydroxide with a 2, not either one of these weird formula. And that charges must be balanced. If we're figuring out the formula for barium phosphate, we need to know that barium is 2+, phosphate is 3-, and we have to do something to balance the charges, and we do that with 2 phosphates and 3 bariums. An ionic compound is composed of a metal or ammonium plus some non-metal anion. And a molecular compound is composed of a metal or nonmetals with some other nonmetal atoms around.